In this section, we'll be taking a look at the ISIS concepts objective of the JNCIP-SP exam. We'll cover a recap of ISIS, multi-level ISIS, route redistribution, and advanced operation. For more detailed coverage of this topic, please check out the Juniper courses AJSPR, JL2V, and JL3V.
In this next set of videos, we're going to explore ISIS, or Intermediate System to Intermediate System. So before we set off on these set of videos, let's recap what we already know about ISIS. So ISIS, like OSPF, is an IGP. It's an interior gateway protocol. And if we were using this in a service provider environment, we'd typically be using it to advertise the loopback IP addresses of our edge routers, and we'd be forming IBGP over those loopback addresses. And over that IBGP mesh, we'd be advertising a significantly larger number of routes than we could ever carry in ISIS. ISIS, again like OSPF, uses the SBF algorithm, the Dijkstra algorithm, to find the shortest path to destinations within the network. And again, like OSPF, within an ISIS network, we are forming adjacencies between neighboring routers. And we're advertising routing information over these adjacencies. This information is structured within ISIS in data structures called TLVs, or type length values. And these are contained within protocol data units. Also remember that ISIS was originally developed to support a different layer 3 protocol called CLNS, and it was only later adapted to support IP routing. It was also later adapted to carry information relating to traffic engineering, so we can use ISIS in an environment to support RSVP. And also, much like OSPF again, we can deploy ISIS in a hierarchical topology should we wish, to constrain routing information on certain devices within the network if their control plane capacity is not sufficient to cope with the routing load required in a flat topology. If you wish to refresh your memory further about any of these concepts, please review the videos for the JNCIS Service Provider exam, also located on this site. In this video, we're going to take a look at multi-level ISIS, which is what we have drawn on the board here. We have 3 groups of routers, and each group of routers is configured with a different area ID. Remember that this is the most significant portion of the ISO address that you have configured on a loopback of a Juniper router. And the main purpose of the area ID is to restrict the formation of level 1 adjacencies in a multi-level ISIS environment. You'll not form a level 1 adjacency between 2 routers that have a different area ID. So we could never form a level 1 adjacency between R1 and R4, for example. And much like with hierarchical OSPF, the purpose of this design methodology is that we're restricting the amount of routing information that's contained within certain areas. So what we have is, amongst level 1 speaking devices, amongst routers that have level 1 adjacencies, we're flooding level 1 link state PDUs. Those link state PDUs do not get beyond that level boundary. So we have link state PDUs for level 1 flooding here, and here, and here, but they're not flooding across these level 2 adjacencies. what instead is happening is that on a router that has both level 1 and level 2 adjacencies, that information from the level 1 link state PDUs is being inserted into level 2 link state PDUs and advertised across those level 2 boundaries. This is what's called a level 1, level 2 router, and it's performing the role loosely equivalent to a ABR in OSPF terminology. And so we have our level 1 routing information arriving at level 1, level 2 routers, being advertised in level 2 link state PDUs across those level 2 adjacencies into other areas and across the network. And much like with OSPF, in OSPF we have the concept of a backbone area, area 0, to which all other areas need to be connected. In ISIS, we have much the same thing. But in ISIS, what we have is the concept of sort of a backbone line of adjacencies. So we need a contiguous line of level 2 adjacencies to form the backbone. And into this backbone, we advertise from all of the separate level 1 areas the routing information. So the backbone has a complete picture of all the routing information going on within the entire ISIS domain. So let's take a look at this level 2 backbone in this case here. You see we have it extending between these three areas, between R1, R4 and R7 here. And we've also got a level 2 adjacency between R3 and R6 here. We need to make this level 2 backbone contiguous. So we also need a level 2 adjacency going on between R1 and R3. So we then have this complete level 2 backbone running across all of these routers. You see that R1 and R3 are also participating with routing in this level 1 area here. So between R1 and R3, we maintain two separate adjacencies. We have a level 1 adjacency and we have a level 2 adjacency. And we can do this in ISIS because we maintain two completely separate link state databases for level 1 and for level 2. So this is how routing gets from a level 1 area up into the backbone. How are we routing in the opposite direction? How are we getting routing information into level 1 areas? Well, you can think of a level 1 area in ISIS much like a NSSA with no summaries configured within OSPF. That is, that we're not advertising any link state PDUs from the backbone into that level 1 area. So how are we going to get reachability out of that level 1 area? Well, this is achieved by using the concept of the attached bit. On any router that has level 2 adjacencies and also level 1 adjacencies, that router in its level 1 link state PDUs sets the attached bit. He's basically saying to the rest of the routers within that level 1 area that he has connectivity to the greater ISIS domain. And when level 1 only speaking devices receive these link state PDUs with the attached bit set, they know that they can route to that device to get to the greater ISIS domain. So they auto-generate a default route pointing to that router. And then when traffic hits that router has a link state database for level 2, so he can route to those external destinations. So that's the key thing to differentiate between OSPF. We're locally generating that default route based on an attached bit, rather than receiving a default route from the ABR due to some configuration on that ABR. One final thing to note about ISIS is that we've talked about this attached bit. And there's also another bit within ISIS link state PDUs that can affect routing, and this is the overload bit. If we wanted to remove a particular router from the network because we were just about to execute planned maintenance, we can set the overload bit on that device. This bit will then be set in any link state PDUs that he advertises, and he's telling the rest of the network to no longer use him as transit to get to any other destination. And this has the effect of removing traffic off that device where the attached bit is configured. In this section, we took a look at the various different components that are present in a multi-level hierarchical ISIS environment. In this video, we'll talk a little bit more about the redistribution of routes between levels within ISIS. So we've already talked about the main rule, which is that we can advertise internal routes from level 1 up to level 2. The level 1, level 2 routers, R2 and R3 in the case of the diagram on the board, are taking information from the level 1 link state PDUs and advertising that across level 2 adjacencies in level 2 link state PDUs. So we are propagating routing information from level 1 to level 2 on our level 1, level 2 routers. What we're also doing is that any routing information coming from level 2 into those level 1, level 2 routers, we are not propagating that information down into the level 1 only speaking devices. We've talked about these two rules before. What we haven't talked about is external routes, so routes that have been redistributed into ISIS. In the case here, we have BGP routes redistributed into R4, advertised in a level 1 link state PDU to R2. Is R2 going to advertise these routes across his level 2 adjacencies? Well, no, he's not. So external routes within a level 1 area do not get up into the level 2 backbone by default. So what if we do want these routes to be propagated up to level 2? What if we do want some routes propagated from level 2 down to level 1? Say we want to advertise this network B down into level 1, for example. Well, to do both of these things, we need to turn to routing policy. So this is going to be an export routing policy applied to protocols ISIS. Remember, it's export because we're taking routes from inet.0 and we're exporting them into ISIS for onwards advertisement within that protocol. And to control routing announcement between levels in ISIS, we have some new syntax to use within routing policy, and that's we can use to and from statements identifying level. So we could be saying we're going to be advertising routes to level 1, we could be advertising routes from level 2. This is additional match and set criteria that we're using within the routing policy framework that we're going to be applying to protocols ISIS export to control routes flowing from level 1 to level 2, or vice versa, from level 2 to level 1. Another thing to mention here is that there's no equivalent concept of area range in ISIS. So if we want to be summarizing routing information to flow between the two levels, then we need to do it manually. i.e., potentially we need to be suppressing routes, and we need to be configuring an aggregate route and matching and advertising that instead. Again, we're doing all of this under the policy framework in a policy statement that's applied to protocols ISIS export. So that's the general flavor of how we're going to be getting routes flowing between level 2 and level 1 and vice versa. But it's also worth talking about a specific corner case. in that when we start playing around with routing policy, particularly when you're starting to redistribute routes, as you've seen in other use cases, there exists the possibility to introduce routing loops. So let's walk through a particular case here where we could potentially get a routing loop when we start to play around with route redistribution between levels. So say that we have this network B on R1, and we want to redistribute it from level 2 into level 1. So this route arrives on R2 and R3 in level 2 link state PDUs. So R2 and R3 are level 1, level 2 routers with some form of policy applied that's identifying this route and allowing its advertisement into level 1. So this route is now announced in a level 1 link state PDU from R2 to R4 and from R3 to R5. And these link state PDUs then propagate network wide. So eventually the route from R2 gets to R3 and vice versa. From R3 it gets to R2. Now we're following standard ISIS rules here. So R2 is going to take a look at that level 1 link state PDU, and it's going to advertise that routing information back up into level 2. And we're going to be doing the same on R3. So you can see here that we're creating a routing loop for network B. So to prevent this situation, ISIS has the concept of a up-down bit. So this bit, under normal operation, say that we're just looking at the standard behavior of ISIS. We have this network A. It's connected to this level 1 area. It's advertised in a link state PDU, and it gets to R2 and R3. Standard behavior is we're announcing from level 1 to level 2. So by default, this network has the up bit set, which means we are allowed to announce this route from level 1 to level 2. To stop this routing loop, where we are redistributing a route from level 2 to level 1, what happens on the level 1, level 2 routers is that we set this up-down bit to down. So what this means is when the route is propagated via those level 1 link state PDUs from R2 to R3 and from R3 to R2, when the level 1, level 2 router receives that link state PDU, he has a look at it and he sees the route for B has the down bit set. And this means that he's not allowed to now advertise that route up to level 2. So the route only propagates within level 1 once it's been redistributed. Thereby, we're breaking the chances of this routing loop existing. In this video, we talked about how we can control route redistribution between the different levels within ISIS using routing policy.
In this video, we're going to talk about some of the more advanced ISIS operations and configuration options. So firstly, let's think about how ISIS and OSPF are similar. They're both fundamentally link state protocols. So they both use the SPF algorithm, the shortest path first algorithm, to calculate the best path to any given device from any given device within an area, within a level. However, there are some subtle differences between the way that the link state calculations are performed between ISIS and OSPF. Because ISIS uses under the hood a different layer 3 protocol, it uses CLNS instead of IP, the neighbor relationships between routers, that tree structure that we're building between devices that we run the shortest path first algorithm on, consists of CLNS addresses in ISIS rather than IP addresses in OSPF. And the way that the SPF algorithm operates in ISIS is that we first run the SPF algorithm against this relationship of adjacencies described by CLNS addresses. And once we have our shortest path tree built, we then perform what's called a partial route calculation. That is, the IP addresses that are associated with a given node in the tree are calculated so that we find the shortest path to those IP address locations. Historically, what this meant was that ISIS had an advantage over OSPF in that if only IP addressing changed on a device rather than its position within the network, then when we're recalculating routing, we would only run the partial route calculation rather than performing a full shortest path first calculation on every device. And this had the advantage of reducing control plane load. As router control planes have increased in power, this is no longer so much of a consideration when you're choosing between OSPF and ISIS. In ISIS, there is also the concept of mesh groups. So ISIS is often used in the core of networks. And in the core of networks, we often have a high degree of meshing between devices. And ISIS link state PDUs are flooded by devices to every other neighbor, every other adjacency, apart from the one that received the initial link state PDU. And in networks that have a high degree of meshing, this can mean that a large number of duplicate link state PDUs arrive on devices, needlessly consuming resources. So if your network has a high degree of meshing, you can use the mesh group functionality to reduce the link state flooding. What you would do is that you would configure all interfaces that are facing devices where we have a full mesh into the same mesh group. And what that means is when we receive a link state PDU across an interface belonging to a particular mesh group, we do not then reflood that link state PDU out to other interfaces belonging to that mesh group, thereby reducing the duplication of these packets and reducing the load on the control plane. Coming to our next advanced option now, remember that when we have a designated intermediate system elected on a broadcast segment, that designated intermediate system is going to be flooding complete sequence number PDUs out on the LAN by a default of every 10 seconds. If you did want to fine-tune this behavior, you would use the CSNP interval option to configure the flooding of CSNPs from the designated intermediate system away from the default value of 10 seconds. And finally, that brings us to the authentication configuration options. With ISIS, you can configure authentication in two different places. You can configure it per level, and you can configure it per neighbor. If you configure it per level, this is going to authenticate every single ISIS packet. That's going to be hellos, complete sequence number PDUs, partial sequence number PDUs, and link state PDUs. And because of this, if you were configuring per level authentication, you would need to do this for every device in that level. The second option, the per neighbor option, we are only authenticating hello PDUs. Therefore, you can do this independently on a per interface basis. Not all devices within the same level would necessarily need to have per neighbor authentication enabled for ISIS to function properly within that level. In this video, we talked through some of the advanced configuration options and advanced behavior for ISIS.